Hi guys, welcome to video lectures. So I'm going to try this and see how it goes. We are looking at what we would have talked about on Friday if I wouldn't have lost my voice on Thursday. So I want to first summarize where we were and think about what we meant by spontaneous. And then we want to answer the question, what is Gibbs free energy all about? And how does it simplify the criterion for spontaneity? So first, let's review a little bit about what we did in talking about total entropy to decide whether or not something was spontaneous. So we had several of these equations to think about, right? First, we could find the entropy change for the system, right? Products minus reactants of the standard molar entropies multiplied by their stoichiometric coefficients. And we could find the entropy of the surroundings using the enthalpy, right, delta H, of the system divided by the temperature at which that happens. If we add all of that up, we can get the total entropy change. And if that's positive, it's spontaneous. And if it's negative, it is non-spontaneous. So let's simplify this, because so far we're talking about a lot of things that we have to find. The entropy of the system, the entropy of the surroundings, and we have to add it all up. So we want to simplify life a little bit. So one thing we could do is just make the substitution for the surroundings into our total entropy equation, right? So that's one step. So now at least everything's in terms of our system or the reaction, right? Delta H and delta S. But to simplify things even further, we're going to define a new thermodynamic variable called Gibbs free energy. And we use the symbol G for that. And Gibbs free energy is just the quantity of the enthalpy minus the temperature times the entropy. And generally, we only talk about changes in Gibbs free energy because we can't actually measure Gibbs free energy. We can only measure changes. So Gibbs free energy, delta G is equal to delta H minus T delta S. We're going to use that again and again. If we divide through this equation by T, right, we'll get delta G over T equals delta H over T minus delta S. So if we look at this equation that I've circled in red and this equation that I've circled in red, let's look back and forth at those. It looks very similar, doesn't it? It looks like delta G over T is just the negative of delta S total. So delta G equals negative T delta S total. So if delta S total is positive means spontaneous, then delta G negative means it's spontaneous. Now here's where I usually would stop and ask you guys if you had any questions. So I want you to pause the video and write any questions down, and we'll talk them over in a chat room later on. All right, so the increase in total entropy results in a decrease in free energy. So I want to show a picture next that shows this, shows what's going on a little bit more. So at constant temperature and pressure, we could think about how Gibbs free energy changes as a reaction or a process progresses. So this means that the Gibbs free energy changes as things happen. So as reactants become products, right? So we could think of this area here as pure reactant and this area as pure product. And we know that things always tend toward equilibrium from what we talked about in equilibrium. So we can now think about this all in terms of this new Gibbs free energy, and the direction of spontaneous change is always the direction of decreasing free energy, because the minimum of free energy is equilibrium, where delta G or dG of this function, right, is going to equal 0 at equilibrium. So everything's always tending towards the minimum delta G. Everything's always trying to get to equilibrium. So this is really what underlies all of trying to get to equilibrium that we talked about last semester. So I want to point out again that delta G changes as it progresses, right? Delta G changes. What we're going to talk about first is delta G naught, right? Or the standard free energy change, which is connected to the standard free enthalpy change and the standard free entropy change. Right? So all of those things are connected via the definition of free energy. So now we find that anything that we have a positive delta G would be non-spontaneous. And if we have a negative delta G, it would be spontaneous. So it's always flowing in this direction of minimizing the free energy. Again, write down any questions and we'll talk about them in the chat room. Whoops. Okay. So let's look at how this affects the phase changes, right? Our simplest kinds of chemical reactions, we can think about our phase changes. So this example, we have calculate the change in molar Gibbs free energy for the process of liquid mercury becoming gas phase mercury. Right? So we're going to look at that in two ways. First at 350 degrees Celsius and then at 370 degrees Celsius. And think about which one would be spontaneous. So first, we've got delta G equals delta H minus T delta S. So we've got the enthalpy of vaporization, right? Delta H of vaporization is 59.3 kilojoules per mole. And the entropy of vaporization, 94.2 joules per Kelvin mole. So I want to convert that so my units work, right? So I have 94.2 times 10 to the negative 3 kilojoules per mole Kelvin. So I find that at 623 Kelvin, or 350 degrees Celsius, I get a positive 0.61 kilojoules per mole for delta G, not spontaneous. If I do the same calculation, only 20 degrees higher at 370 Celsius or 643 Kelvin, we find that we get a negative delta G, right? A negative 1.27 kilojoules per mole. So it is spontaneous at 370 degrees Celsius, but not spontaneous at 350 degrees. So this leads us to think about the thermodynamic origins of phase changes. So let's look at a few phase changes. So we can look at this plot of Gibbs free energy as a function of temperature. Right? So we find that at low temperatures, the Gibbs free energy of the solid is lowest. So the solid is most stable. As we increase the temperature, the Gibbs free energy of the liquid becomes lower, so it becomes most stable. And if we keep increasing the temperature, for water at least, the vapor phase, right, the free energy of the vapor phase becomes most stable. That wasn't the case for carbon dioxide, right? Carbon dioxide doesn't exist at regular pressures as a liquid. So if we look at the way the solid changes and the liquid changes and the vapor changes in terms of free energy as a function of temperature, we find that the solid is most stable. And at regular pressure, the liquid is never lower in free energy than the solid or the vapor. Okay. So now we're thinking about factors that favor something happening spontaneously, right? So it all depends on whether it's exothermic, negative delta H, or endothermic, positive delta H, or entropy is increasing or decreasing. Right? So we look at this whole table, and really we're just looking at that delta G equals delta H minus T delta S equation and thinking about how that connects. So how we can find this, how do we find the standard Gibbs free energy of a reaction or the reaction free energy? So we can find the free energy of formation of reactants or products. And those I just noticed should probably be deltas in front of there. We can think of them, if we could measure just G, we could find this. If we could measure the free energy of pure reactants and pure products. The trouble is we can't measure that. We can measure changes in the formation of reactants or products. So keep in mind that G, right, our free energy changes as a reaction happens. So we'll think more about that over the next couple of units when we're thinking about how will that affect how much work we can get out of something in electrochemistry, and if we're thinking about how we tie this all back to equilibrium, and we'll talk about that in a few weeks. Okay. So thinking about the formation, the free energy of formation of anything, we've got elements in their most standard state, most stable form, standard state. We have to set that equal to 0, right? So that the delta G of formation of elements in their standard state is 0, just like we did for the enthalpy of formation. So thinking about changes and how that works. If we do that, then we can ask this question. How could we determine the free energy of formation values? But don't we already have tables of delta H of formation and delta S? Or at least we have the molar entropies, standard molar entropies. So let's do an example where we actually find the delta G. So if we have the reaction where we are forming cyclopropane, right? So calculate the standard free energy of formation. Well, we know whenever we're making any compound, we always start with elements in their standard states. So to make the cyclopropane, we're going to need solid carbon and gas phase diatomic hydrogen to make the cyclopropane. Then we can find the delta H of formation of cyclopropane in our table, right? We need to look that up, and we find that it's a positive 53.30 kilojoules. We can find the delta S of this reaction, right, by doing products minus reactants. So 1 mole of cyclopropane minus 3 moles of times the standard molar entropy of carbon minus 3 moles times the standard molar entropy of hydrogen gas. Right? So if I place those numbers in, so I need to look these up in a table. So I get 237.4 joules per Kelvin for this and 5.740 joules per mole Kelvin for the carbon and 130.68 joules per mole Kelvin for the hydrogen gas. We calculate that out. We find that delta S is negative 171.86 joules per Kelvin. So to find delta G, we're going to use our definition of delta G. Delta G is delta H minus T delta S. So that is going to be equal to our 53.30 kilojoules minus our temperature, 298 Kelvin or 25 degrees Celsius, times our delta S in terms of kilojoules per mole. So we find that the delta G here is a positive 104.5 kilojoules. Questions? Write them down. We'll come back to them in a chat room. So typically, this is where I would ask you, and I'm really missing you guys because it's really weird just talking to a computer. But this is where I would ask you, what does that mean, right? Why positive 104 kilojoules? What does it mean? What does the sign of delta G tell us about our cyclopropane, right? So looking at this table, this chart, so we've got the Gibbs free energy of formation of a couple of compounds. Right? Some of them are positive, some of them are negative. So if we say the elements are 0, right, so then anything with a positive delta G of formation means it's unstable compound relative to its elements. Right? So a positive delta G indicates that that compound is not as thermodynamically stable as its elements. If we have a negative delta G of formation, then it is more thermodynamically stable compared to its elements. Right? So water, silver chloride, and ammonia are more stable than elements. I think this is nitrogen dioxide, hydrogen iodide, and benzene are less stable. So here's a small table And we've got that benzene in here again as being positive. And we've talked about benzene before, and it's come up before that it is positive. So that means it should decompose into carbon and hydrogen gas, right? The elements. But it turns out it doesn't, because there are thermodynamically unstable compounds that survive for long periods of time. And these are called inert or non-labile. So non-labile, labile refers to the thermodynamic or the tendency that is realized. Whether it's thermodynamically stable or unstable, it still depends on the kinetics of that happening, how quickly it happens. Okay, one more example. Let's calculate the standard Gibbs free energy of the reaction of the formation of glucose and oxygen from carbon dioxide and water, right? The thing that plants do. So we can get this from the Gibbs free energies of formation, but we want the reaction energy. What's the free energy of the reaction? So similar to before, we're always going to do products minus reactants. So the Gibbs free energy of formation of the products minus the Gibbs free energy of formation of the reactants, all of course multiplied by their stoichiometric coefficients, will give us the Gibbs free reaction energy. And these are all standards. So first we find, products, right? My glucose and my oxygen minus reactants, carbon dioxide and water. So I need a table. I need to look these up in the table. So those paper tables I gave you guys will be really handy for this. So for the glucose, it's negative 910 kilojoules per mole. For oxygen, it's 0 because O2 gas is an element in its standard state. For the carbon dioxide, it's negative 394.36. And for the water liquid, it's negative 237.13 kilojoules per mole. So once we figure that all out, we find that delta G of reaction is 2,878.94 kilojoules. So what does this mean? It means that this reaction is not spontaneous, right? That plants that do this reaction are doing work, right? It doesn't just happen spontaneously. We can't just grab carbon dioxide and water out of the air and make glucose, right? It takes some work. Okay, so for more practice, after you watch this video, Activity 18 is on the Sakai site, so you should download that and practice doing all of the activities so that you've got this down.